Hi. So it gives me great pleasure to introduce our next speaker, Damek Davis. He's, as you can see, is a faculty at Wharton Statistics and Data Science Department. Prior to that, you were at Cornell in Operations Research and Industrial Engineering. His PhD was from Department of Mathematics in UCLA. And we are delighted to have you give these lectures.
Thank you. Okay. So thanks for the invitation. It's my first time to India at all. So I'm really enjoying it so far. I saw a lot of Bangalore on the way in because the driver got lost, but it was like really, different experience for me, and I'm really enjoying it so far. So, so today I just wanted to give you a talk that has kind of like one neat idea in it that I've been kind of exploiting in different papers. And the idea is, the goal of the idea is basically to accelerate gradient descent in problems that are sort of beyond the classical setting that we've studied in optimization, where we have complexity theoretic guarantees. And so in order to tell you about that, I just want to start with a very simple optimization problem where there's kind of like a mysterious behavior. At least it was mysterious to me a couple of years ago. So the setup is you have access, you basically have access to a matrix M star. It's positive semi-definite. And from linear algebra, we know that whenever you have a positive semi-definite matrix, you can take a square root of the matrix, meaning you can write it as an outer product of some XX transpose, where X is now a matrix which is sort of like maybe tall and skinny, depending on the rank of the matrix M star. And as long as sort of the width of the matrix X is bigger than M star, you can always factor this matrix. And so the way you would do this, classically is using something like an eigenvalue decomposition. But this is an optimization talk, so we're just going to throw away sort of these linear algebra tools, and we're going to focus on using gradient descent type methods to factor this matrix. Okay, so it's just a very simple problem that kind of motivates the theory that will come ahead. So the optimization problem that we're going to minimize here is just trying to penalize the measurement misfit in the Frobenius norm. So just take the difference of the sum of square entries. Okay. Now, this optimization problem has very different behavior, and algorithms for this optimization problem have very different behavior, depending on the sort of width of the matrix, whether it's skinny or whether it's very wide, or whether its width matches exactly the rank of M star. Okay? So when the width of this matrix is less than the rank of M star, we can't fully factor this matrix, so we're going to ignore that case. So instead, let's suppose that we're in the situation where we can actually get access to the rank of M star, which is not actually realistic before you run these methods, but let's say that we have that. So if you know the rank of M star, and you've set up your problem here so that you're optimizing over D by R matrices, then you'll find very quickly that as you run gradient descent, you will find a solution exponentially fast. Okay? And so what I'm showing you on the y-axis here is the distance to the optimal solution if you can't read it. The x-axis is the number of iterations, and you can see just very, very quickly we approach like numerical precision. Okay? The situation changes pretty dramatically as soon as you misspecify this rank. And I'll call this the exact parameterization setting because the number of parameters in the matrix X is exactly the number of parameters you need to specify the matrix M star, which is D times R. Now, as soon as we over-parameterize this problem and increase the rank by, say, M star plus 1, what we will find is that gradient descent with, let's say, overestimation of the rank by 1, which is shown here in this blue curve, what we see is that the speed of convergence of these plots slows down exponentially. Okay? It just becomes this very kind of slow, what we call sublinear plot. The situation only gets worse when we move to rank 10 or rank 15. Okay? So it just continues to slow down. Now, what I'm running here is just gradient descent, this classical algorithm, right, with a constant step size that I chose, the one that you would usually use in theory. And so you might be thinking, well, we have so many more optimization algorithms today than we used to have in the past. So why don't we just try all of those and see whether we see a similar phenomenon? Is this just a problem with gradient descent? And what I did is I took all the algorithms in PyTorch, or most of them that were implemented, and I ran the same setup where I set the rank to be the true rank plus 5, so just 5 over parameterization. And you can see that while all the methods are making progress and some make a little bit more than the others, they all sort of plateau or slow down eventually. Okay. And you might think that this is like a problem with, let's say, how we chose the parameters for these methods, but the same behavior persists if we do like a grid search over all possible like step sizes and hyperparameters inside these methods.
Actually, this is very interesting. Also, this runs counter to the general perception that over-parameterization helps convergence. So do you have any comment on that connection?
So I don't think this has much to do with generalization at this stage, because we're just dealing with, I mean, there's no notion of like prediction or classification accuracy or anything like that. So it's a bit hard to map it on to the setting of whether over-parameterization helps or not. But what we know, and I'll show an example with like a toy neural network later, that shows that even in those problems, even if you have access to the population loss, you still have this sort of slowdown. So it's a persistent issue. It's not something that will shed light on whether generalization improves with over-parameterization. Yeah, it just slows down the optimization, the problem. Yeah. That's a good question. So what if R is less than the rank of M star? In that case, I forget what the behavior is. I think it should converge to some, I mean, you're not going to get zero loss, first of all, because you can't factor the matrix. So it will probably, I think it should still converge linearly to the loss level that you can get. But I'm not sure. I would have to run that again. But I think it should, my intuition is that that should happen. Yeah, good question. Other questions? Yeah. This is a behavior across all matrices that are not full rank. Basically, if you over-parameterize by 1, you always see this behavior. Yeah. This is with random initialization.
Condition number of M star doesn't play a role, I think was the question.
The condition number will play a role in the rate of convergence, but it won't play a role in like, yeah, it'll be like a constant that appears, yeah. Other questions? Okay, so so I just want to tell you a little bit about like how we can get around this bad behavior with what turns out to be a pretty minimal change of the gradient descent algorithm. But to do that, I want to just take you back to sort of optimization class sort of 101 and remind you of like what determines the speed of optimization algorithms. Okay? And so if I were to pick a single number that influences how fast an optimization algorithm converges, it would be the rate of growth away from the minimizers of the function. Okay? So what do I mean by that? So let's consider a function f, and let's see how fast it grows from its minimal value. Then what we call here is the rate of growth is this power p. Okay? Now, most optimization problems that we care about grow with some power p away from their solution set. Okay? Most of the problems that we care about have that property. And classically in optimization, we have mainly studied the case where p is equal to 2. This is the case of quadratic growth. The reason we really like this case is because we get very fast convergence. We get exponentially fast convergence. And so for those of you who have taken optimization, you've seen like strongly convex functions. That is an example of a function with quadratic growth. Now in this talk, I'm not going to restrict to convex functions. I'm going to mainly be thinking about this type of growth. Okay? So if we knew that we had quadratic growth, we'd be in good shape. And in fact, when we're dealing with matrix factorization and we have the exact parameterization, then the function does have quadratic growth. It's possible to show that. It's not too difficult to show that. And so you would expect to see this super fast convergence, even though it's non-convex, but locally around a minimizer, you would expect to still see this very fast geometric convergence. Now, what goes wrong when you over-parameterize is that the growth of the function drops from 2 to 4, okay? So now instead of having quadratic growth, we have quartic growth. What this means is that the function is now much flatter, at least in certain directions. Okay? And you can see this from this landscape here. This isn't exactly matrix factorization, but it's sort of the same geometric picture that you'd expect. Now, the problem is that when we go from quadratic to quartic growth, it's known that there's, at least in terms of the existing optimization methods, that there is sort of an exponential gap between the speed of these two types of gradient descent on these two types of problems, okay? So when I was making these slides, and I think even all the way up, this is till 2020, the best possible rate of convergence I could find for gradient descent under quartic growth was something like 1 over k to the 4th power, which is not too bad, but it's still sort of sublinear, right? Compare that to gradient descent, and you see that there's an exponential gap. Okay. Now, the intuition for this, just 1 second, the intuition for this is just like, imagine you have a ball in your graph, and you're rolling it around. If I start on the sort of very flat side, it's not going to move very far, very quickly. Okay, so you're going to be in trouble. Now, I'll show you a little bit more obstructions that you can expect to see in these problems as we go on, but that's sort of the basic idea.
My question is just, why do you have p equal to 4?
Ah.
Isn't it that, there's some eigenvalues that should go to 0, and you're looking at the growth of this difference away from 0, right, of x?
Yeah, so if you are
Why is it
able
important?
to, yeah, it's a good question. So if you are able to identify those eigenvalues that should be 0 beforehand, the eigenvectors, and you just optimize in that space, you will have the right growth. It will no longer be flat. But if you cannot, then you are always dragged down by that growth. So part of the hard part of this problem is identifying that space accurately enough. And that's one reason why that problem would slow down. Yeah. And that'll come up as we go through the talk, but that's sort of one idea. Yeah.
Measure p, it depends on how you parameterize the space of functions you're looking at?
Yeah, p will depend on that, yeah.
I see, somehow, okay.
Gradient descent is not invariant to parameterization, unfortunately. Newton's method is closer, but not quite. Yeah. Other questions? The bound is invariant to what? Unitary transformation, correct. Yeah, so the question is the bound is invariant to unitary transformations. If you have a diffeomorphism and you precompose the function with that, it will be invariant. If you don't have a diffeomorphism, like if your Jacobians are not full rank, et cetera, then you will lose an order of growth on this side, still, potentially. Yeah, that's one way to describe for that problem. That's why it would be 4th order growth, yeah. Yeah, good question, yeah.
Good question about this picture, about the second picture.
Yeah.
So I can see that, so in one direction, I can see that the function is growing quite fast, maybe along this direction. But along this direction, it doesn't seem to be growing that fast, or maybe just a visual.
No, this function is deliberately plotted like that. So that's a good point, right? So, so exactly what the question was pointing out was that if you somehow knew what the bad space of eigenvectors was, right, and you could kind of force them to 0, then you would be in the quadratic growth setting. And so this is like, you can kind of think of as maybe like kind of the nuisance direction, and this is like the actual direction that you want to optimize. Right? So optimization problems often have this kind of weird mixed structure like this, yeah. Yeah, good question. Any other questions? Yeah. 0 is a critical point for this problem, so you won't move anywhere, yeah. Okay, so so the question, of course, is can we close the gap? And I'll show you our approach to doing that. So we're going to basically just make one change to gradient descent. We're going to change the step size to be adaptive to the problem, okay? And so what do I mean by that? The algorithm that we introduced is called GD-Polyak because I was not being creative with names when I wrote this paper. It basically combines gradient descent with an occasional large Polyak step. So it looks like this. We have an inner outer loop structure In the outer loop, we have I steps. And for each one of those steps, we are going to run gradient descent with a constant step size, something similar to what you would run if you only had a function which was like a quadratic. Okay. So we just run that, very, very similar step size, not too small. When you're done running those k iterations, what you do is you take one large step. Okay. Now, the way I'm writing this step is in terms of what's called a Poliak step size, which is a very popular step size in optimization for like a number of years. You can ignore the exact form of it for now. It's just a very convenient sort of like closed form solution for the type of step I'd want. You can really just think of this as a very large step size. Okay? We'll come back to that as we go through the talk. So what we were able to show is that if you run this method and you start close enough, or you eventually reach a neighborhood close enough, the type of behavior that you will have on smooth functions, right? Like let's say, for example, C5 functions, that I think what I need in the end. And you have quartic growth, right? Very specific quartic growth. Then your loss is going to decay at almost a geometric rate. This is like an almost linear convergence. Okay? So what's different from the quadratic case in terms of this convergence rate is that the exponential here, usually what you would like it to depend on is the total number of gradient evaluations that you've computed as you've run such methods. Okay? So you'd like this to depend on k times I. Since we're running this inner-outer loop structure, we actually have a really different dependence, which is actually much worse in some sense, but it's still exponential. We have the minimum of k and I, right? Not the product. Okay? And so it's very important that when you run this method, you choose not only the inner loop step for a very long, like to be very long, you need to choose sufficiently many outer loop steps as well. Okay?
If you had quadratic growth in the functions, would you have any degradation or will it still perform well?
I think it should still be this, it should still perform well, yeah. It won't be as fast as like the fastest methods for quadratic growth, but it'll behave like gradient descent, yeah. So this is only for quartic functions, yeah. So you have to enter a small enough neighborhood of the solution for this behavior to take effect. It will depend on the function. It doesn't depend on the dimension, but it depends on like sort of the certain growth properties of the function. We don't have a handle on exactly how to get those because you'll see how the neighborhood sort of arises as we go through. Yeah. I'll come back to that in just one second. So that's a good point. So the question was step size depends on minimum of f. So I'll come back to that in just one moment. Okay, so this guarantee, it only applies to quartic functions, and we'll see sort of why that is as we go on. But let me just show you how the method behaves. So if we take this same overparameterized matrix factorization problem, you'll see that if you run the method, which is this kind of one that's going down, you have a staircase structure. You see long periods of the plateau, followed by a rapid drop. The plateau is when we're running gradient descent. The rapid drop is the one large Poliak step. Okay? And this is the general way the curves look. They always look like this when you plot them. That will become apparent sort of why that structure exists as we go on as well, symmetrically. Yeah. That's a really good question. So the other question was, why not just go all in on Poliak? We'll see what issues that causes later, okay? So this is like, everyone is foreshadowing like really, really well. So I really like this. This is good. So we'll come back to that. So as we go through, we'll see what's special about quartic growth. We'll come back to that as we go. To answer the question that was over here, what about this minimal value? So Poliak step size needs a minimal value. But in recent years, people have figured out how to adapt such methods to only rely on a lower bound on the minimal value. So for example, in machine learning, when you're trying to optimize a loss, 0 is usually a lower bound. The convergence rate will degrade a little bit here. There will be like an extra outer loop factor, but it'll be like, if you think about the global behavior, it'll be exponential to the minus cube root of the total number of gradient evaluations. So, so you can basically estimate this as you're running the algorithm. It's possible to do that. Okay. Okay, so let's just show a couple more experiments. The first experiment is just a small sort of generalization of the matrix factorization problem. So for a number of years in like the sort of non-convex optimization for signal processing literature, people were working on this problem called matrix sensing, which is very similar to the matrix factorization problem, except there's usually some sort of linear map built on top of the matrix, meaning that you don't observe the matrix M star itself, but you observe its dot product with a number of random matrices AI. Okay? In this case, I'm looking at the absolutely most simple version of this problem, where the AI themselves are Gaussian matrices. And for this problem, you can prove that the loss function has quartic growth, okay? And it's clearly a smooth function, it's C infinity, right? I mean, it's a polynomial in the end. So this is a problem where the theoretical results will apply. And so what you can see is two things, right? So we can run gradient descent with a constant step size, and this is the type of behavior you'll see, sublinear. You could run Polyak step size, and what you'll see is that it decays pretty quickly, but then it sort of levels off. So this is the question that you were asking just a minute ago. And you could see the GD Polyak method, which sort of combines the best of both here, and then kind of like it surpasses both, and still has this staircase value. So what's going on at these like random drops, right? So in order to see what's going on with these random drops, we should look at the step sizes, right? So in gradient descent, we have a constant step size, which is shown here at the bottom. The entire time is just constant. For the Polyak method, we see that the step sizes are kind of all over the place. They go from like below the constant step size all the way up to almost 100,000, right? But if you look at this GD Polyak step, what's going on is that you take a very, a certain number of, I guess, 300 gradient descent steps with a constant step size. And then in between those, when you take this Polyak step size, you shoot up. And you shoot up so fast that you're actually growing exponentially as you run this algorithm. Okay? It turns out that that sort of behavior is like necessary for making these things go quickly. You'll have to take a very, very, very large step size, yeah. So the step size here shown in blue, it's constant in between these two, and then it continues growing, right? So it's like it's constant, it's down here, and then it goes like that. So that's how the step size is behaving. Yeah. Yeah, the GD is the shelf or the stair. And then when you drop, that's the Polyak step, yeah. Yeah.
So for the GD Polyak steps, it also has a GD element in it, right?
Yeah.
So those are still in blue, not purple, in the step size graph.
Here. Yeah,
But
yeah,
no,
those
no,
are all
step
shown.
size.
Yeah, all the steps are shown. Is that what you're asking?
No, in the step size graph.
Oh, here, yeah.
Yes.
Yeah, yeah. So, yeah, these are the GD steps, these blue. And then I'm using the same step size for both.
Okay,
Yeah.
that's what I wanted.
During the constant period, same step size.
Okay, yeah, that's
Good question, yeah. Oh, 1 second, feel the mic, yeah.
Yeah. So my question is, how does the GD Polyak, the whole algorithm performs when you, with respect to K, like what happens when you decrease K and what happens when you increase K, like the constant number of steps?
That's a good question. That will become clearer as we go, because there's going to be a geometric structure that appears as we go that will give you a better sense of that, yeah.
It's actually related to my previous question about parameterization.
Yeah.
I mean, since you said earlier the growth was dependent on parameterization, are these other results also dependent on parameterization? For instance, if I try to parameterize this whole problem in terms of a unitary matrix and the eigenvalues of X.
Oh, okay, yeah.
Rather than just looking at the matrix entries of X, I could do that. I mean, would you get the same kinds of results, or is the result sensitive to the parameterization?
I think then, since I think there, you would get the same type of results, because what will happen is that the lower bound for the growth, right? It only depends on the spectral, because up to a change, because it's unitarily invariant. So you could diagonalize. I actually don't know. I'd have to do that parameterization and work that out. But yeah, it's not a common one that I've seen here to break up the eigenvalues and the unitary matrix. I haven't seen that parameterization here. But yeah, that would be an interesting thing to try. Yeah, I don't know. I don't know actually off the top of my head. Yeah.
Gradient computation might also be not easy, right? Because you have to compute on that manifold perhaps, and then maybe project.
Yeah. Yeah, you could implement it, but it would, yeah, I'm not sure.
So perhaps a stupid question. So what is good about like exponentially growing step sizes? Like as you approach the minima, it should like, you should take smaller step sizes, shouldn't you?
You'll see in just a moment. Yeah, that's a good question. So what's special about these big step sizes, right? Okay, so that's a really good point. We'll come back to that in just a moment, okay? And then I'll just say let me just give one other example before we get into what's going on. So the other example is the most toy version of a neural network problem you can come up with, okay? So back in, I think, 2023, Simon Du had a paper called Gradient Descent, or Overparameterization Exponentially Slows Down Gradient Descent for Learning a Single Neuron, okay? So what he found was that, you would expect for these problems that you get exponentially fast convergence, but you get a sublinear convergence rate, okay? This is the problem he was studying. You're trying to learn this V from like measurements of its dot product with Gaussian random vectors. And you assume that you have access to all the Gaussian random vectors. You have basically population level access to the distribution. But you have one twist here, is that you don't know how many of these V terms there are. And so you're going to now over-parameterize. You're going to take a sum of multiple, let's say, ReLU type functions to approximate a single neuron, okay? Now, even in the case where you have over-parameterization by 1, in this paper, Simon showed that gradient descent will exponentially slow down. You'll have like a sublinear convergence rate, and you do see that in the plots, okay? And this was all for the population loss. None of this is actually a viable or a good idea for stochastic optimization, but at the population level, this is what happens. Likewise, if you run Polyak, you'll see it's very noisy. It eventually kind of saturates and hits a sublinear rate. But this GD Polyak is still converging quickly. And as you can see, you still have this sort of bizarre behavior for Polyak where it oscillates wildly, getting about 100,000 for its maximal step size. And GD Polyak is growing exponentially. Okay. So the question that was just asked here is like, okay, so now I'm telling you take big steps, right? Why don't you just take big steps? Okay. And in fact, taking big steps is a good idea for certain problems. Okay. So let's take the most simple function that has fourth order growth, which is just a single variable, x to the fourth, right? We're going to look at this function. Now imagine that you try to apply gradient descent to this function. Okay. So gradient descent, if you write down the recurrence that you get, you can write it in sort of closed form here. What it does is it takes your current iterate, right? And recall, it's trying to push it to 0 because 0 is the minimizer. It takes the iterate and scales it down by some factor which is less than 1. Now imagine that you take that factor, the step size here, to be constant. What's going to go wrong? Okay. If you take this to be constant, the factor that you're scaling xk down by is converging to 1, right? And it's not bounded below by 1. So you're not getting this geometric convergence that you'd want. In fact, you can show that if you choose this a to k to be constant, the rate of convergence that you get eventually is something like k to the minus 1/2. And this is the sort of plot, but it's actually hard to see. A better thing to look at here is how quickly the distance is decreasing. Okay. Now, if we knew this recurrence exactly, we would know how to set the step size, like analytically, right? We would just choose the step size to be 1 over xk squared, right? We converge in one step. That would be a great thing to do. But we don't know this step size. We don't know that the recurrence looks like this necessarily, so it's more realistic, I guess, to think of choosing this to be a constant factor times xk to the minus 2, okay? And if you do that, you're going to converge exponentially fast, right? The interesting thing about this is that if you look at the Polyak step size, the Polyak step size is exactly x to the minus 2 over 4. Okay. Yeah. No, 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 because if you took it to be x squared, it would be even smaller. It would go even slower. Oh, okay, but then you would have to periodically reset it over and over again. You would have to continuously reset that smoothness parameter, right? So the smoothness parameter is typically taken as like a global smoothness parameter, not as an adaptive step size. I agree that if you could get that in this case, that would be great, yeah. But this is not even to make a comparison with gradient descent. It's just saying that you need to take big step sizes. That would be a perfectly good way to take it, yeah. Polyak just picks it out automatically, which is nice, yeah. So you had a question? Yeah.
What happens when we reach convergence? I haven't seen a graph like reaching convergence. So the f minus the min term should go to 0 in the ideal case. But I'm assuming because we don't have the min, you're using some other, I think.
I'm using the min in this case here, but I can, in all these examples, I know the min. Yeah.
If you know the min, haven't you already solved your problem?
No, the minimal value, minimal value. Do you mean the actual minimizer of the problem?
Yeah.
Yeah, these are toy problems, right? So I'm just like trying to demonstrate it on problems that have quartic growth. Yeah.
So we can't implement this if we don't know the min.
No, no, we can. So,
so
we can implement it if we have a lower bound on the minimal function value.
Okay.
That's all we need, yeah.
And then what will happen to like the exponentially growing step sizes when we kind of get close or reach the point?
They get bigger, they keep going.
So
keep going.
that would kind of, like because it's going, it'll overstep maybe and.
Well, recall, this is the step size that we're using. This is blowing up as you approach the minimizer. This never crosses the minimizer. It's always on that size.
Oh, got it.
Right?
Okay, yeah. Okay,
so the point is
makes
here,
sense.
these gradients are going to 0 really, really, really quickly. So you have to boost them up using a big step size. Yeah, so you won't move anywhere otherwise, yeah. Okay? And then I'll just say these are, you're still having the same phenomenon of exponential growth. Not so important, so. Okay, so in higher dimensional problems, the geometry is not this simple, unfortunately. In fact, people have known for a long time that there are like obstacles in the domain when you try to optimize like, higher dimensional functions. And these are typically called ravines. So in this plot, what I'm showing you is sort of like a ravine that if you were to run gradient descent or let's say Polyak, what happens is that you sort of quickly reach this area and then suddenly you're kind of trapped near it. You kind of have to glide onto it as you approach the solution, right? You don't know that this exists. You don't know how to get access to it, but your algorithm is attracted to it and it has to kind of hug it as you go, which is like annoying because you can't go fast then because you're stuck there, okay? And if you look at the qualitative difference between gradient descent and Polyak, they're pretty similar. Gradient descent follows it more closely. Polyak will bounce around a little bit, but it's still following it closely. And if you dig into their actual rates of convergence, you see that while Polyak is much faster in this case, they're both converging sublinearly. The step sizes also sort of stay fixed at a certain level, although at this case, I think that says 10 to the 6th. I can't read it, but it's a really big number, right, when you're running this. But they do not increase exponentially, okay? And so these objects, these ravines, have been sort of in the background of optimization for a long time. The earliest sort of mention of them that I've seen in literature is a paper by Gelfand and Settlin in 1961, where they talk about ravines. This paper I actually had a hard time getting a hold of for like, a year or two. I emailed everyone who had written a summary of it. So, several of them died while I was trying to reach out to them, unfortunately, and so I couldn't get access to it. But then a student at Stanford found it for me. And so I read it a couple, maybe like 6 months ago, finally. And it was exactly as in the description. So the first place that I saw this written about was in a paper by Boris Polyak. And he wrote down the ravine method in this form. Okay. So what does the ravine method do? Well, what it does is it alternates between gradient steps. Okay, let's say we do one gradient step, and what's called a ravine step. Okay. What's the idea here? The idea is that you want to take a gradient step because that will hopefully bring you to the ravine. Once you're on the ravine, you want to continue in that direction. You want to have momentum along that direction, okay? So this momentum term plays the role of a tangent vector to the ravine, right? It's kind of hopefully going in that direction, okay? And it's an early precursor. This method, you know, it should look familiar to some of you if you studied optimization. It's a precursor to several very important methods in optimization, such as Polyak's heavy ball method and Nesterov's accelerated gradient method. In fact, Nesterov's accelerated gradient method is kind of like, I don't know, you reverse the order of the steps, and it's very, very similar. I think Atouche and Fedeli figured this out some number of years ago. So this method has been around for a long time, and in the original paper, this is the picture that they had, okay? Which is interesting, because it's exactly sort of the picture that we were looking at just a moment ago. So what happens is you're at a current point, you do some number of gradient steps. We don't know how many, but we do something. We get to a point that's like on the ravine or nearly on the ravine. And then we take a momentum step to reach the next point, and it will take us up here. But let's say that we've actually done 2 so far so that this looks a little bit simpler. So we're here, we get to the ravine, we use the previous point on the ravine and the current one, and then that takes us off of it. We go back, it takes us off of it, we go back. Now in this picture, this is purely a one-dimensional like algorithm. So if you read this paper, it says that we don't expect this to generalize beyond this one-dimensional ravine valley. And the reason is that while you have these sort of access to these kind of tangent vectors, they may not point in the direction of the gradient anymore, right? They may not point in the direction of decrease of the function. And so what was shown in this paper was mainly the essence of like how such an algorithm should behave, right? Where you alternate these steps, but not the existence of a ravine, and not whether you actually converge more quickly or anything like that. Yeah, question? That's a good question. We don't. So this paper, I think, it's very much like a sketch of an idea, right? It's like a brilliant sketch of an idea where you get to a point that you hope is near the ravine, and they're very optimistic if you look in these pictures. They hope that as you take these steps, you don't get that far from the ravine, so you only need one more step to go. That's not true at all, actually, if you implement this. Sorry? Yes, yeah.
I'm interested in this.
I have no idea. I have no idea why they're doing that. Yeah. Yeah. Yeah, maybe mandatorily enforced, I don't know. So anyway, so this is sort of like the precursor to this method. Okay, so the question is whether like such structures are real, right? Because we've seen them in a couple of examples, but are they like actually always there? And so what we showed in this paper was that ravines always exist as long as you have 4th order growth for your function, and your function is at least, I think C5, maybe C6, but you know, you're sufficiently smooth. Okay. So intuitively, we call a set in the domain a ravine if it's smooth, and in directions normal to the ravine, you grow sharply, and along the ravine, you're flat. You have sort of a flattish behavior, okay? How do you get it, right? So a bit more formally, these flat directions come from the null space of the Hessian, right? Those are the directions in which the function has minimal curvature, or at least the curvature is vanishing as you're approaching the solution. So you look at the Hessian at the solution, it has a null space. Those directions are sort of like the ones where you don't expect the quadratic growth. If you look at the orthogonal complement of those directions, that's where the Hessian actually has full rank within that subspace. And you should expect to see sort of like quadratic growth in those directions, okay? Now, that's sort of the sketch of where they would come from, but it doesn't tell you how to build the ravine. So to build the ravine, you can kind of do it in a, let me show you how to trace it out at least. Okay, so here's the function we've been looking at. If you look along the u-axis here, those are the directions in which the function is flat. That's like the subspace parallel to like the null space of the Hessian. Now for each one of those vectors u in the null space of the Hessian, right, one of these, you can form a slice of your function f, right? Now that slice is going to have a Hessian which is non-degenerate at its minimizer. So in fact, the function is locally strongly convex. This one-dimensional slice of your function, which is shown in red here, okay? So it has a unique minimizer. And so in order to form the ravine, we can trace it out by looking at all directions in the null space of the Hessian, considering the slice of the function along that point, and then minimizing that slice. That will give us access to all of these points along this parabola here, okay? So this is one way to think about it. This is what we called in the paper the Morse ravine, because it comes from this lemma called the Morse lemma with parameters. It's just a consequence of the implicit function theorem. So it's pretty easy to sketch out, but it exists. So this is kind of like maybe an abstract geometric picture. If you're more comfortable with sort of the more computational algebraic framework, we can actually construct explicit ravines for the matrix factorization problem. Okay? So let's say that we want to minimize this function still. What we're going to do is, without loss of generality, assume the matrix is low rank, right? And has is basically diagonal. This is fine to do because the norm is unitarily invariant. It doesn't really change the character of the problem, right? Then what we'll do is break up the variable x into sort of the good part p and the nuisance part q. If we write down the loss function, it decomposes into 3 terms, right? We're going to group 2 of them. The first part is going to be the sharp part. It corresponds to like an actual exact parameterization, matrix factorization problem in the first term, plus some noise, okay? In the second term, we're going to call that the flat part. From this decomposition, you can get the ravine. So the ravine itself is just a set of minimizers of the sharp part, okay? This is the part that you grow quadratically towards. And the flat part is exactly a pure coordinate function, right? So it's literally just like x to the 4th. It looks like the single variable x to the 4th function we were looking at before. Now, this is one ravine, and the construction that I showed you on the previous slide was also just one ravine. It turns out there's always infinitely many ravines. The only difference is they're all tangent at the solution. They all look pretty similar, but they can all just kind of like, if there's like a little O of distance to the manifold perturbation, as you approach that solution, then this still will give you a ravine to the set. So you can kind of perturb it a little bit. Did you have a question? I saw a question up there, yeah. What is this? PQ transpose. So PQ transpose is trying to make P and Q orthogonal, right? Yeah, you're trying to get rid of the nuisance part, yeah. Yeah, so that's a really good point. So if you look at this decomposition, these 2 parts are kind of orthogonal, right? They're kind of like orthogonal functions in some way. I don't know how to say it. Maybe the best way to say it is that their gradients are almost nearly orthogonal as vectors, okay? So it's a useful exercise to think through, like, what could you do with an optimization problem if you knew it was like, maybe like, let's say it was separable in 2 variables, or like the variables were coupled in a loose way like this, okay? So it turns out that whenever you have a ravine, you always have an orthogonal, sort of nearly orthogonal decomposition of your function into a flat part and a part that grows sharply away from the solution. Okay. So how do you get it? So here, M is my ravine. And what I'm going to do is take M, and I'll take our function f, and I'll look at its behavior along M, and then I'll just radially extend it out, okay? You can think of this as like the smooth extension of the function. It's kind of like taking the function and precomposing it with the projection onto the manifold, okay? That's what this flat piece is. It gets rid of all the quadratic growth in this direction. It's just purely flat. Okay. On the other hand, whatever is left over is going to have this sharp growth, because the Hessian of this is going to be 0, and this will take up the entire rest of the Hessian. Okay. And so what we've done is we've taken this manifold and we've decomposed the function into smooth, flat pieces and sharp pieces, which are nearly orthogonal. Now, when you look at these 2 problems, based on what we've talked about so far, you know that gradient descent behaves very differently on both of these functions, right? For example, if we just had the sharp piece, this is a function that has quadratic growth to its minimizers, right? The minimizers are just the manifold. And so if we run gradient descent with a constant step size, you're going to see fast convergence, in fact, linear convergence to the minimizer. If you run gradient descent on the flat piece with small step size, you're in trouble. It's a fourth order growth function. It's going to be slow. But if you run it with a Polyak step size, or at least like a geometrically increasing step size as you approach the solution, you're going to find fast progress tangent to the ravine. So now you have this kind of like tension between the two, right? On the one hand, if you want to make progress on this part of the objective, you need to take a small step size. If you want to make progress on this part of the objective, you need to take a large step size. And anytime you take a large step size on this function, you're going to screw up all your progress on this sharp piece, because you're just going to get pushed away from the manifold. This one's going to be in good shape, but this one's going to get pushed away. Okay. So the key idea of this GD-Polyak algorithm is that, well, while you get pushed away, you're not pushed away so far that you can't recover by a few steps of gradient descent. And by few is an exaggeration. You should be thinking of like few as in like a square root of the total budget that you have. So you actually do have to be pretty accurate. Okay, so just to restate the algorithm, we're going to take many small steps of gradient descent and then take a single Polyak step. So this is the sort of behavior you'll see. All those are the gradient steps, big Polyak step, and you're kind of bouncing off. But within each of these parts where you're going back to the manifold, you need to take a lot of gradient steps to actually get close enough. And why do you need to be so close? I'll tell you why you need to be so close. So basically, we want to be close enough that if we take a Polyak step on the full function f, that its behavior is basically equivalent to the behavior on this very flat part, or the tangent part, ft, right? Right. We just want it to look like that in those directions so that we make a ton of progress. Okay. Now, once we take that, once we get to that point, which we don't detect, we don't like check for it, but if you choose k large enough, it will happen. Once you get to that point, you will make tangent progress. But like I said, you get pushed off the manifold, and then you have to take a bunch of steps and go back. Okay. All right, so this is how the method works. You can try it on this sort of function that we were just looking at, and you can zoom in to see the qualitative difference between Polyak and this function. So you see Polyak, as I'm zooming into the manifold here, eventually just kind of gets stuck. And this one is still taking a pretty constant step size, at least step length, as we're going relative to like how close we are. Whereas this one's just kind of getting left behind, which is interesting to compare the two. Okay, so yeah, do you have a question? Okay, good. Yeah.
What happens if you try to adaptively figure out whether you are on a ravine or not?
So yeah, that's a good question.
Is it
People have
bad?
tried to do that for a long time. It's hard to do that. There's not a good test that I know about, other than you can, so here's what you could do. You could look at the Hessian, and then you could see whether you're like, you put it like a threshold for the eigenvalues. If the eigenvalues go below a threshold, then you could say, okay, I'm like very close to the ravine. That's the way you should think about it. No, that won't actually be enough either, because the Hessian, those eigenvalues are decaying as well.
What if you just see on your gradient steps how much it's moving? If it's not moving too much, then it's probably on a ravine.
That could be the case, but the question, I guess,
But
is what would it buy you?
so simple. Yeah.
Yeah, what would it buy you, I guess, to know you're on the ravine?
Let's say you have some methodology that tells you that whether you're on a ravine or not.
Yeah.
Perfectly. I don't know how you have access to that, but
Yeah.
how fast will that be compared to this?
So what you would want to do there is then take us, okay, so what you would want to do there, I think it would be similar. I think it would be similar.
I see.
Yeah, it would be similar, I think. I think it might be similar. Yeah, I haven't tried that. So something like this exists. There's like a non-smooth version of this sort of property, which is called an active manifold. And people for a long time have tried to like try to figure out when you get on that active manifold. And you can prove that you can get very close to it. And then the idea there is like you use some like second order information to speed stuff up. But here, I don't think you're going to do much better than just, you might improve the convergence rate, which now is exponential to the minus square root of number of gradient evaluations to exponential to the minus gradient evaluations, which is a lot, but I don't know how much it would help.
Still exponential.
Yeah, I don't know. That's a good question. I'm not sure how I would leverage it any better. Yeah, it's a good question. I'm not sure. Yes.
I also have a question. You said Hessian.
Yeah.
Instead of taking this Poliak step, could you instead just have done one second order step using the Hessian? Would that be equivalent basically? Because that would give you the same kind of scaling of step size if you were close to the quartic minimum.
One would hope. It's hard to prove it.
That's
don't
somehow
think
more
we ever proved
systematic, no?
Yeah,
Because
yeah.
that's
One
kind
would
of-
hope that happens, but
Okay.
it's hard to prove it. I think we tried to prove it then, but there were some minor obstacles, I think, and then we just like got busy with something else. So I'm not sure if it's doable
I
or
see.
not.
And
Yeah.
it might also avoid this problem that you just explained of kind of going off when you're on the ravine. I haven't thought about it carefully enough.
Uh-huh.
But if you use the Hessian, maybe it doesn't push you up in the other directions. No?
Potentially.
Maybe that's just wrong.
I think you're still going to have some force in those directions in the gradient, right? You're going to have some component in that direction. But that's a good question. Yeah, I don't know. Yeah, here the goal was really to use a purely first order method.
I guess like any second order method like that would also depend on smoothness of the Hessian, because if the Hessian suddenly changes, then
I'd
like
be
the-
fine if you assumed it was C infinity or
So,
anything
yeah,
like that.
my question was like, what are the assumptions under which like this result works?
This works as long as you have, I think it's C5 or C6, I forget, but it's one of those two. It's not, nothing higher than that, yeah.
I guess as long as it is in C3, like even the Hessian should be stable enough and
Yeah, but the C5 will basically guarantee that we have some ways to compare our function value on and off the manifold in a nice way. So you'll see there's like an assumption in the paper called assumption A. So it's the only assumption, I guess. And we prove that that holds when you have this property, and that's what we need, yeah. But we need C6 for that, I think. C5 or C6, I can't remember off the top of my head. Something like that, yeah. Okay, so just to wrap up, because I guess I have 2 minutes. So so all of this was stated for fourth order growth. So the fourth order growth basically allows you to do the following thing. So the Hessian is basically, in some directions, it's very small, right? And if you assume fourth order growth, you basically can say that, well, it's not, the function is not, like what's left over after you take the whole quadratic part is at least growing at a fourth order rate. That's where fourth order bit comes from. And we stated the result as a result for fourth order growth functions because it was just cleaner. But the result does extend to any function that sort of looks like this, where you take x squared plus absolute value of y to the p for any p greater than or equal to 3. Now, x squared plus y to the fourth is sort of the way you should think of these functions, how they behave. But the p equals 3 case, funnily enough, was exactly the type of growth that you get in this neural network example. And in fact, this neural network example it's not even C5, C6. I think it's like C2, maybe. But the manifold is simple enough. It's just a subspace. And so we could just push the result through without having to assume all of that. But sort of the p equals 3 case is showing up here. Okay, so the point of this talk, basically, in sort of this line of research, is just to kind of nudge people into thinking about more like finer local regularity properties of optimization problems, and like how to use them to exploit, how to exploit them to design faster algorithms with, in this case, a very minimal change. So we have this, very like well-developed complexity theory since, the 80s for convex optimization, but it's hard to go against like the limits of like Nemirovsky and Nesterov's results unless you are able to sort of analyze some new geometric structure. And like they exist in some sense, right? I'm gonna give myself 2 seconds. They exist in some sense, right? They exist for quartic functions and potentially even beyond that, although that seems very hard to prove. And even in non-smooth optimization, there are notions of ravines that exist for non-smooth functions, but there the separation isn't between quadratic and fourth order, it's between first order and quadratic growth. That's where sort of the difficulty lies in analyzing these algorithms. So the hope is, you analyze or you isolate these geometric structures and you use them to speed up these algorithms so we're not stuck with very slow algorithms in your solution. Of course, I'd love to make these like stochastic, more applicable to machine learning algorithms. It seems very, very difficult without further assumptions. But hopefully it's a useful starting point for other people to look at. And I guess that's all I have. So thanks for listening.
We can take a few questions.
So every time you move out of the manifold, you take several gradient steps to come back. So I mean, is this number of gradient steps constant as you?
No. So the guarantee, right? So the guarantee was should be here. So the guarantee was that the number of gradient steps I take, k, factors into the exponential in a minimum. So ideally, the number of steps you take is comparable. The ones that take you towards the ravine and the number of Poliak steps, right? So those two should be comparable. Basically like square root of your total budget. Yeah, you really need that. Yeah, otherwise you don't see the speed up because like the point is that you need to get close enough to the manifold that your function looks like a fourth order function. And if you don't get close enough, then you're not going to see that. I don't think it's 0 on the manifold. I'm trying to forget. It does. The Hessian gives you the tangent directions, yeah.
If you use that information, maybe like, I mean, you can reach the manifold even faster.
Yeah, if you had that information, you wouldn't have to do anything with the manifold, I think, because you would know the directions in which the function was kind of behaving like fourth order. Like if you get close enough, you'll see a clear separation of the eigenvalues. There'll be like big ones and then ones that are like tending to 0, right?
Yeah. Using the big ones,
Yeah.
those eigenvectors you can.
Those will make you go down, and then if you use the small ones and just take steps in that subspace, then you won't affect the other ones that much.
So
there'll be some effect, but you won't affect.
So I'm just asking, like, instead of alternating between Poliak steps and like this vanilla gradient descent steps, why don't you use like, I mean, is there a way to use to leverage the Hessian more?
Yes, I think so. It's just we didn't want to do that because we wanted a purely first order method. But yeah, if you could compute the Hessian, if you're happy computing the Hessian, then you could use it, yeah.
Even if you.
Oh no, if you have complete access to the Hessian, I think your behavior will still be linear, but it'll be much faster. I think it will depend less on the condition, because there's like multiple notions of condition numbers here. There's like the condition number for the quadratic part, the condition number for the quartic part, and they all interact. And I think the Hessian would alleviate some of the dependence on the condition.
What is the condition number?
Condition number would be like the Lipschitz constant of the gradient divided by the constant in front of the quadratic growth. So like the more spread, the bigger that is, the slower algorithms are. Usually algorithms like slow down with that. Yeah.
I see.
So I think Newton's method will just buy you less dependence on those, which is huge. Like that's much faster if you could do that. But then you have to compute a Hessian, which is dimension dependent, and that's not easy yet.
Yeah, so if I'm understanding it correctly, the key takeaway is if you just do GD, then you'll get stuck in the Raven. So you need to do Poliac so that you move on to deal with this flat part, and then you will reach the solution. Yes.
Exactly. Yeah.
Oh.
Yeah.
to answer, but so another place where this kind of quartic growth shows up is this whole area of robust linear regression, where instead of the square of the residual, you take the fourth power or some higher power.
Yeah.
And there again, you have slow convergence because of similar issues, if I'm not mistaken.
Mm-hmm.
And then I guess I'm just wondering if one could use such a method to accelerate those things.
I think if you have fourth order growth, yeah, I mean, anything with fourth order growth, you could accelerate. That's a polynomial essentially, right? So this robust linear regression idea.
Yeah.
Right. Yeah. So I think you should be able to do that.
Yeah. So are you aware of if this has been explored? This, or maybe it's too recent and maybe nobody has tried this.
So, sorry, the echo. I can't hear what you're saying exactly.
So I'm saying that there's whole area of robust linear regression where you take the residual and you take the fourth power or a higher power and not just the second power, which is usually considered. So there also, I suspect that the rates are slower because of similar reasons that you described.
Yeah.
So I'm wondering if a technique like you said could be used to get new results and better results for the.
That would be interesting. Yeah, I'm not like an expert in that literature, but that would be interesting to see that. Yeah, I think it should. I mean, as long as you have fourth order growth, it should. But I'd have to see the exact optimization problem to check. But yeah, I think that would be very interesting. Yeah.